going to talk about a different type of electrochemical cell, and that is electrolysis. Now, electrolysis is quite different from galvanic or voltaic cells in that the reactions are not spontaneous. You need to use a battery or some power source. So why bother? Well, the reason is we use electrolysis to do a lot of useful things, like produce some pure metal. So as you know, most of the metals in group 1 and 2 and even some in group 3 are metals that are so reactive they're not found naturally in nature. So a lot of things of these metals are mined, and then the compounds that they're part of have to be separated in order to produce pure metal. So for instance, you could actually take something like sodium chloride, which you can mine, and use electrolysis to separate that into sodium metal and chlorine gas. The other use of electrolysis is electroplating. So if I wanted to put some gold plating on something or some silver plating, I can use this to put a thin layer of a desired metal on top of another metal object. Alright, so let's take a look at electrolysis. So I want to contrast, first of all, the main differences between voltaic cells, also known as galvanic cells, and electrolytic cells. So first of all, the most important thing is that voltaic cells, these are acting as batteries, and by the nature of the natural reduction and oxidation reaction, they are spontaneous. Okay, if they are not spontaneous, the battery won't work, whereas electrolytic cells are not spontaneous. The voltaic cells generate electricity, whereas the electrolytic cells require electricity. They will not work unless you give them some energy. So it requires electricity. Now, the voltaic cells usually have two half cells. Not always, we've been drawing them with a salt bridge. But you can also have a porous plate that separates a cell that allows the salts to go from one chamber to the other. Okay, so usually voltaic cells you'll see as two separate cells, or you'll see as this porous membrane. Whereas in electrolysis, you will often, not always, but you will often see just one cell. Sometimes they'll be separated, but usually it's just one cell. And then they both have electrolytes. Okay. In voltaic cells, we generally use reactive electrodes, where in electrolytic cells they are inert electrodes. The thing that is different also is the cathode in a galvanic cell is positive, whereas the cathode in the electrolytic cell is negative. The anode is negative in a voltaic cell, but it is positive in an electrolytic cell. So one of the things you'll see here is this energy. The energy is being produced by the cell. In this case, it lights up a light bulb, or we'd have a voltmeter here indicating how much voltage is being produced. And then we have a battery here which is providing the energy to make this process of electrolysis work. Okay. So as we look at the parts of the electrolytic cell, it's important to know that anode is always defined by where oxidation occurs. So it doesn't matter what type of cell, the oxidation occurs at the anode, and the cathode is always defined by where the reduction occurs. And the other thing is, because this is a non-spontaneous cell, the electrolysis is using energy, external energy, to force the electrons to move in an unnatural, not the way that they would normally move, unnatural direction, and they are moving from positive to negative, which is, as you know, is not the way electrons would typically flow. Now, it is important to note that in electrolysis, the mnemonics still work, an-ox. So the anode is where oxidation takes place. Reduction is where the cathode occurs at the cathode, and the electrons move from anode to cathode. Alright, sometimes I'm given this symbol, which would indicate a battery, and the large line can be split into two to make a positive. So that's how I think about it being positive, whereas the smaller line is going to be my negative side. So if I make this positive, this is going to be my anode, because remember it's positive here, and the electrons are flowing. They're not flowing from negative to positive like they naturally would. They're flowing the opposite way. So they're going to flow from positive to negative. So this will be my cathode, and the electrons will be going in this direction. Okay, from anode to cathode. This is where my oxidation is occurring, and this is where my reduction is occurring. The big difference is, though, the electrons are moving in a direction that is contrary to what they would normally do. And the only way that will happen is you will push them using electricity or a battery. So let's take a look at what would happen if we were using this electrolysis to separate sodium chloride. And this should not say solid, it should say liquid, because you need to have the ions able to move. They need to be molten in order for the ions to move within this solution. Okay, so we're going to talk about taking molten sodium chloride, and then next slide we'll look at what happens if we have aqueous sodium chloride. Molten sodium chloride is pretty straightforward. We have NaCl starting as a liquid, and we are going to produce sodium metal and chlorine gas, right? So we're going to go from sodium plus 1 electron to sodium. Unnatural to do that, right? Sodium is not going to want to give up is not going to want to take on an electron. And chlorine minus, 2 chlorine minuses are going to become Cl2 plus 2 electrons. So this is, I'm gaining an electron here. So this is my reduction, and this is my oxidation. I can look at the standard reduction potential sheet, and I see that this is minus 2.71 volts, and that the sodium, that's what the sodium reaction is, and then the chlorines is negative 1.36 volts. So they're both negative, and if I add those together, I get 4.07 volts. Okay, and so that's how many volts I need to make this process happen. Okay. Okay, so the electrolysis of aqueous salts, those in water, are more complicated than doing it for molten salts, because the sodium and the chloride ions compete with the ions that come from the self-ionization of water. And if you remember, I get H plus and OH minus from the ionization of water. And I have, of course, sodium plus and Cl minus from the ionization of sodium chloride. So these are all the ions floating around in the solution. So let's orient ourselves. Here's the positive side of the battery and the negative side. Okay, so this is my anode. It's where oxidation takes place. This is my cathode. This is where reduction takes place. So my positive ions are going to be attracted to my negative electrode. So we're going to take a look at both reductions, and here they are, hydrogen becoming hydrogen gas, and the sodium ion becoming sodium. And you can see the reduction for sodium ion to sodium metal is very unfavorable. So what's going to happen is the hydrogen will get reduced instead. So what I'm going to end up with is I'm going to make hydrogen gas. I'm going to see bubbles forming from that gas as it's produced. So I will not get sodium metal. This will not happen. And as it turns out, no group 1 or group 2 metal, when in a aqueous solution, will be reduced. Hydrogen is always going to happen preferentially because the sodium ions are so stable, it's very, very difficult to get them to reduce. Now what happens at the anode is a little bit more complicated. You can't just simply look at the oxidation values by flipping these. There's a concept called overvoltage that gets involved that's beyond the scope of the course. But I will tell you that chlorine gas is what gets produced at the anode.